In this video, I am going to create a function that will allow us to add a node at a particular or a certain index of our linked list. So far, we have the ability to add a head node or an ability to add at the beginning of the list. We also have the ability to add at the end of the list. We also have a print list function and a function that counts the number of nodes that we have. On the right hand side is a pictorial representation of the linked list created with these various functions that I have on head. Data wise, I've decided to go in increments of 10, 20, 30, 40. And so what I plan to do is I plan to add the number 5 at any one of these indexes or in between these indexes. And in the red are the index numbers. So this is index 0, index 1, index 2, index 3. So if I wanted to add this new node into index 1, well, 0 would point to it, and then this would point to index 1, which will become index 2. And so this will become index 3, and this would become index 4, and thus this will become index 1. The first thing that I want to do is I want to create a function prototype, and this is going to be a node type. I'm going to call it push at index. For this function, we are going to have 3 parameters. The first parameter is I am going to use a double pointer. So we are going to use call by address. And then I'm going to add the index number or the desired index in which we want to insert a node to, and then the data that we want to insert. So I'm going to copy this prototype and create a function definition for it at the bottom. The first thing that I want to do is I want to create a node. And that step is going to be similar to how we've always created nodes. And I'm going to take that from our last function and copy and paste it. And so this is our node creation. And this is the blueprint for our node creation. What we do is we create a new node. We use the heap to create it by using malloc. This is just our error check to make sure that we don't have a heap overflow. And then here we insert our data into our node. For our next, we set that to null. So when we call this function, it's going to look like this. If you look at the right hand side, at the bottom left hand corner at the red, we are going to insert the address of head, which is the head pointer that is in our main function. If we want to insert this at index 2, we are going to insert it in between 1 and in between 2. So this is going to become the new 2, index 2. This will become index 3, and this will become index 4. And the data that we want to insert is 5. So it will be easier to distinguish where our 5 is located, since everything is in increments of 10, 20, 30, 40. So increments of 10. So far, all we have is a creation of our node, which is this one, which will allow us to use the malloc function and create a node inside of our heap memory. Before I even start coding, let's take a look at the logic. For this function, I want to create 2 pointers. I want to create a head pointer, and the head pointer is always going to stay at index 0 because the head should always be the first node of the list. The second pointer that I'm going to create is the current pointer. The current pointer is what I'm going to use to traverse. So when this traverses to here, then this is our current pointer, and if it traverses to index 2, then index 2 becomes our current pointer, and if it traverses to index 3, then index 3 becomes our current pointer. So current is the node that I'm going to use to traverse. So let me go ahead and create the current node pointer in our function. So this is going to be a current pointer, so star current, and then we're going to set that equal to star head. Remember, this is a double pointer, and so every head in here must be a star pointer. The next thing I want to create is I want to create a index. I've already used index here, so I'm just going to call it I. And then we're going to set that equal to 0. So this right here, the index I, is basically our red numbers. So currently, index I will start out at 0. And I'm using these index numbers because this is how an array is indexed. And so I'm going to keep it similar to that. So an array and a linked list technically mirrors each other. The only difference is an array is a contiguous set of memory block, whereas linked list is all over the heap. And that's why I draw it this way. It's not a straight line. It can be anywhere in the heap. Our list that uses the pointer is pointing or allows us access to each node. So for example, this is pointing to 200, this is pointing to 300, this is pointing to 400. And that's what their next link pointer value is holding, the address of each node. And remember, all a pointer variable is an address variable. And so when you think of pointers, think of it holding an address, because that is the only thing that it can hold. I hope that this is clear and to why I set it equal to 0. Now, there also has to be a way for us to measure our bounds, in that if I wanted to add an index -1, well, there isn't an index -1. If I wanted to add to index 5, well, there isn't an index 5. Those would be out of bounds. But good thing we've already created a count node function, because a count node function keeps track of the number of nodes that we have on our list. So in this case, our count node will return 1, 2, 3, 4. I'm going to create a variable called number of nodes. And I'll just abbreviate it for number of nodes. And I'm going to assign the count nodes function to that. And here it's going to be a star head, because we have a double pointer, and a double pointer is a pointer to a single pointer. And so what this does is this will return an integer and set it or assign it to num nodes. And in this case, it's going to return 1, 2, 3, 4. There's 4 nodes, so num nodes technically equals 4 right now. This function will come in handy once we set the bounds for our linked list. Let's go ahead and get the first condition out of the way. So the first condition is it's always if the list is empty. We'll design it to where if the list is empty, regardless of what index number that they assign to it to insert to, it's always going to be our first node. And so how do we know if our list is empty? Well, easy. If our head is null. If our head is null, then we're going to assign head to new node. That will address our very first condition. So in this case, if we have an empty list, then this index 2, this won't matter. Our first node is going to be a 5. This head will just point to that, and so will our current. Now let's target our second condition. For our second condition, what if I wanted to add to our index 0? So if I wanted to add this node here, then what should I do? Well, this is really pretty easy, because this is the same thing as our pushhead function. Basically, if we're adding to the head of the list, we can simply just call our head function. So in this case, we're just going to type else if, and in this case, if they type in index equals 0, then all we want to do is push head, and we want to use the push head function. And in this case, we want to enter head. So let's test this condition. And so we want the address of head. And there it is. So we added it to index 0. For our next condition, a situation that we have to think about is, what if a user tries to add a -1? Well, our index always starts at 0, so that would be out of bounds. What if our user tries to add a 5? Well, if we only have 4 nodes, that's also going to be out of bounds. Let's create a code for that condition. Our first index always has to be at 0. And here we define this to be our actual index count. So else if, and here we're going to say index is less than I. Anything less than 0 would be out of bounds on the left side, but on the right side, anything more than the number of nodes, because we can insert at index 4, that's just adding a tail node, but anything outside of our number of nodes would be out of bounds. And so how do we type that into code? Well, this is where line 217 comes in. We know that the number of nodes is counted by this function. And in this case, it's going to count 4, and it's going to return 4 because it returns it as an integer into num nodes. So num nodes is holding the number of nodes. this will become 4. Here for our logic, if our index is less than 0, which is on the left side here, so negative, anything negative, or index is greater than number of nodes, then all we're simply going to do is print index request is out of bounds. And here I'm going to put 2 new lines just to make it look pretty. And here we're going to say I and num nodes. And the reason why I did it this way is because I could have typed all of this in one line, but because I want to show this screen as well, I decided to break it up into 2 lines. And in order to break it up into 2 lines, you just use quotes. But this is the same thing as 1 line, or this is the same thing as that. But because I want to be able to show this, I've decided to break it up into 2 lines. Tweeners, let's test this condition. So here I'm going to put -1, push it index -1, so it should print out of bounds. Yes, index request is out of bounds, must be between 0 and 4. Let's try it with 5, and that's greater than the number of nodes that we have. It has to be between 0 and 4. Okay, because if we wanted at index 4, then we're simply just adding a tail node. While we're at it, let me test the first condition, that if our list is empty, it should just add to our first node regardless of what index we put it in. And so in this case, we'll put it at 5, but right now our head is null. We don't have a list. We have an empty list. And there it is. It's going to create it. So far, we've created a node and we've tested this condition. If head is null, it just creates our new node. If our index is at 0, if we want to insert it at index 0, then we're just using our push head data, because that's all that is. We're adding it to the head. If we're trying to add it outside of our bounds, which is negative, anything in a negative or anything more than the number of nodes we have, it's going to print out this error message. Our last condition is if we are adding at any index inside of our bounds. So if we can add it at index 1, 2, or 3, or even 4. Order has to matter. So let's talk about the logic. So say I wanted to add this at index 2. What I would have to do is, if I wanted to add it right here in between these two, the first thing I have to do is I have to traverse our current to our next node or our next index. So I have to traverse it to that. Okay, so that's the first thing we're going to do. And while I'm traversing it, as long as we set current to current.next, it's going to keep going. So when does it stop? It has to stop when our index, I, does not equal index. And it has to be index -1 because I starts at 0. For example, if we want to insert at index, so what we have to do is, we know that I is at 0. And we also know that the index that we enter is going to be 2, but 2 minus 1 is 1. So I does not equal index. True, so let's traverse. So it goes here. But once it goes here, we have to increment I. This is going to increment to 1. Here it's going to say 1 does not equal 1. Well, this condition is false. And so once this condition is false, we can stop traversing because now 1 is equaling 1. And so we want our current to stop here. All right, so let me code that. Since this is our last condition, I've used if, else if, else if. Here I can just use an else. And inside of else, I want to use a while loop. So we're going to say while I does not equal index -1, then we want to traverse current. But we also have to increment I. So we're going to say I plus plus. Once this becomes false and we exit out of our while loop, this is where order matters. So here we are trying to insert at index 2. So we exit out of this while loop because 1 does not equal 1. So that's false. And so now what we want to do is this is where we want to do our insertion. but this is where order matters. What we want to do is we want to set the next, this part, to 0x300. We want it pointing to there. Well, how do we get it to point there? Well, current's next is 0x300. So we're simply going to assign new node's next, which is this, to current's next. So let's code that. So we're going to say new node, and we want the new node's next value, arrow next, and we want to set that to current. And the reason why we want to do it that way is we don't want to break these links. Because if we set this wrong and one of these links are broken, say this link is broken, then we don't have access to these two nodes. They are going to be memory leaks in our heap. And if we get enough of these memory leaks, that's going to trigger our error check. And we're going to get an error saying memory is not allocated, and we won't be able to create a list, or at least complete a list. That's why we want to set the new nodes next to the current next. So now they're pointing at the same thing. So now what we want to do is we want to take this pointer and set it to the new node. And so what's going to happen is we can now set this to here. So now this is going to hold the address 500. Now our index is 0, and this is index 1. This becomes index 2. So I'll just say this becomes index 2. This becomes index 3. And this becomes index 4. If you notice our link, they're all connected. So now let's type that code in. So we want to set our current next to new node, the address of the new node. We're going to say current arrow next equals new node. Let's test this. So let me insert this at index 2. Make sure I didn't make any errors. So let's run it. There it is, at index 2. Let's put it at index 3. Here it is at index 3. Actually, let me make this a little bit more clear, because I know I have node 0, 1, 2, 3. This is meant to be an index, but let me make that more specific. So let me go to my print function. Here I'm going to say node, but I'm going to say index. And let's just test the whole thing. So we'll start at -1, and I'll just go down to 1. So -1, we're going to get out of bounds because it has to be between 0 and 4, because the number of nodes is 4. Let's go to 0. So this is just adding a head node. So that's this condition. So we just tested this. Now we're going to test this condition. There it is. We're adding it at index 0. Now let's add it to index 1. And we already saw this as well when it's out of bounds. So now we're going to test this condition and put it at index 1. So I'm just going to go down to 1. We're putting it at index 1. Let's add it to index 2. There it is, index 2. Let's add it to index 3. Let's add it to index 4. Let's add it to index 5. That should be out of bounds. It's out of bounds. Now let me add another tail. Let me push tail. So now we ought to be able to insert at index 5. And there it is, at index 5. Let me put it at index 4. There it is. So the key thing is order matters. This tells us when to stop current, this condition. And then once we are stopped, and we know because I does not equal index anymore, and the reason why we have index at -1 is because our actual index starts at 0, and whereas our index, it starts at 1. So we need to really match our index. Once you get here, you must first set the new node's next to whatever current is pointing to, or current's next. And then once you have that set, you can take this link, and then instead of being set to here, you can set it to the new node. So now let me go up here. So in the past videos, we've created a call by address, everything that has a double pointer, but we've also created a return the address. And the push at index, let's create one. At this point, I'm just going to modify what we currently have. So let me create a function prototype first, and we're going to call it index1. And since we want to return an address, we have to make this data type a address variable. So that's going to be a pointer. And here we're not going to use a call by address. We're just going to pass the address of head. And let's go ahead and create this function because it's almost identical. The only difference is we're going to return the address of head. So I'm going to copy this whole function and I'm going to put it right below it. So I'm going to make this a pointer and I'm going to put a 1 right here and I'm going to make this a single pointer. The node creation remains the same. But what does change is we no longer have to put a star in front of our head inside of the body of our function. So this just becomes head because this head is basically this head. And so double pointer points to a pointer. And since this is no longer a double pointer, we don't need to make our head inside of our body a pointer. And here we have head again. So this becomes just a regular head without the star. And then here where we have our push head data, since this becomes a call by address, we have to put the address of head here. So because this is inside of, otherwise we'll just get some funky values if we don't do it this way. And then our error check remains the same. And let's see. And then finally our while loop remains the same. And then the only difference is here we're going to return the address of head. Let me compile this to make sure that there isn't an error and that I didn't forget anything. Okay. So expected, so I'm missing, oh, okay. So I'm missing a semicolon. So let me compile that again. Okay, so it's working. So now, since this is returning an address, let me comment this out. And the way we would call it is very similar to how we call that. Let's insert 6 for this one, so that way you can see the difference. So now let's run it. So this should be out of bounds. Index request is out of bounds, okay? Now let me just go down the list. Everything, the logic is the same. The only difference is we're returning an address. So let me hit 0. Puts it at index 0. Let's put it at index 1. Let's insert it at index 1. There it is. And I'm just going to go down to test all of our condition. Index 2. Index 2. Index 3. Index 3. Index 4. And then index 5. And there's our 6. And let me put it at index 6. So this should give us an out of bounds. Out of bounds. You notice how similar our call by address functions to our return the address functions. So this is just using the current address of head in our main function and not making any changes to the address of this head. Now when we return the address, this head's address changes. And so that's the only difference, but the algorithm is the same. And because I've already explained how these work, the logic is pretty much the same. And as I've said, the only difference is one, we're calling by address, and the index 1 functions or any functions that has a 1 at the end, we're returning that address to the head in our main pointer. And that is our push at index function.